I'm going to go through is the ones on this optimization worksheet. So that is attached to today's notes. So what I would encourage you to do is to do these questions on your own. I've already done question A. So I think that's quite a nice question to do. And sorry, just don't do question the one with the milk bottle. Which one is that? I. Don't do question I. We don't want to upset the vegans there. So no, just it's. I thought it's a nice question. It's not actually that great. So don't do question A and the one with the milk bottle. Do the rest, please. And then I'm going to just go through all those examples. So after you've done it and you just want to check it, you can just roll it through. Okay. Right. So example, the second question there, B. We need to enclose a field with a rectangular fence. Okay, we have a 500 millimeters. We have 500 meters of fencing material. So funny laughing all on your own, eh? And the building is on one side of the field, so yeah, you don't be silly and go and put fencing around the bricks. So determine the dimension of the field that will enclose the largest area. Okay, so what do we know? So let's look at those parameters that's been given to us. So P, in other words, is equal to, we've got 500 meters of fencing. So in other words, we've got that plus the X plus the Y is equal, we can make up 500 meters from that. So in other words, 2y plus by x. So 500 is equal to 2y plus by x. Okay. Okay, next part is we want, and then they ask you, we have determine the dimensions for which the field will enclose the largest area. So our optimized equation is all to do with area. Okay, so the area of this field is going to be x times by y, right? That's the full area. Okay, so, and then that's as normal, we just need to find either x or y alone. So 500 minus 2y, we substitute that, of course, into that x there, right? Or if you got y alone, you substitute the x value back into that. So therefore, we've got a is equal to, what is that then? 500 minus 2y times by y. So therefore, and don't be confused now between ax is y, that's just the variable y, right? So ay is equal to 500y minus 2y square, and we're just going to find the derivative of that. So that is our optimized equation, right? That's the one you want. So optimized function, and so the derivative of that will be 500 minus 4y. So 0 is equal to 500 minus 4y. 4y is equal to 500. Y, therefore, is equal to 125 meters. All right? So, and that would mean, so if this is 125 meters, that's 125 meters. Therefore, x is going to also equal to, x is going to equal to, that's 250, that is going to be 250 meters. Therefore, x is going to equal to 250 meters. You just substitute, well, into there if you want to. So it's 500 minus 2 times by 125 is then equal to 250. Okay, so that's going to do it. And then determine the dimensions of the field. Okay, and that's exactly what we worked out. So x is equal to 250 meters and y is 125 meters. All right, here's one of those doers questions. It's a box. So we want to construct a box with a square base, and we only have 10 square meters of material to use in the construction of the box. Assuming that all the material is used in the construction process, determine the maximum volume that the box can have. And then, so because it's a square base, it is a square base there. So because it's a square base, we know that length is equal to width. So don't do this. So just say, well, that is then the width or the length on the length. I don't know. So, okay, here we go. So what do we have? So we only have 10 square meters of material to use. In other words, 10 square meters here is then the total surface area is equal to 10 meters square. All right, so therefore the total surface area here is going to equal to, well, let's work out the total surface area of one of those sides, of one of those edges here. So that is H times by W. Right, so H times by W, and how many of them will there be? There's going to be, well, that one, and that one, and that one, and that one, right? So there's going to be 4 of them, plus, and then, of course, that square base, right? And that one is, of course, plus W square. So the total surface area is going to equal to W squared plus by 4HW. Right, so, and we know we only have 10 meters square there, so that's W squared plus 4HW. Okay, so that's great. Then the other, but now what are they actually asking? They want to find the dimensions for which there's a maximum volume. So that's to do our optimized function is involving volume. So the volume is going to equal to, what is that? Length times breadth times height, W times W times by the height. Okay, so that's the one we want. So you're either now going to get H alone or W alone from this baby here, from those parameters. So if I get H alone, so it's 4HW is equal to 10 minus W squared, so 10 minus W squared divided by 4W is equal to H. So therefore V is equal to W squared, and then we've got this in terms of H, so 10 minus W squared over 4W. So V then is going to equal to W squared divided by 4W is equal to W over 4, right? Times by 10 minus W squared. Hopefully that makes sense, yeah? So we just divide W squared by W. And what we've got then is we've got 10W minus W cubed over 4, right? And if you want to split those terms, that's 10W over 4 minus W cubed over 4, okay? That just makes that, if we're going to find the derivative a bit later, a bit easier. So that is 5W over 2, 5 over 2W minus W cubed over 4. Okay, so that's our optimal function. Okay, so optimized function. And what we're going to do now is, of course, and that is, so VW is equal to 5 over 2W minus W cubed over 4. Okay, and then we're just going to find the derivative of VW is equal to 0 and solve for those W's. So the derivative of VW is equal to 5 over 2 minus 4W squared over 4, right? Oh, no, what am I doing there? Sorry, that is 3W squared over 4, and that is equal to 0. 3 over 4W squared, so that's 3 over 4W squared is equal to 5 over 2. And you just simplify this, you multiply by 4 divided by 3, so that's 20 over 6W, oh, no, 20 over 6, multiply by 4, right? It's 20 divided by 3, it's then 2 times by 6, so W squared is equal to 5 over 3. So W is equal to plus or minus the root of 5 over 3. A negative with length here will make no sense, so therefore W is equal to the root of 5 over 3. And then what is the length then going to be? Or the height then going to be? Therefore, if we're going to work out the height, it's going to be, height is going to equal to 10 minus W, so that's that root of 5 over 3 squared divided by 4 times by root of 5 over 3, and then you're going to get also the root, if you can just type that in your calculator, you also get 5 root 3. And then they ask you, therefore, what is the maximum volume? Maximum volume. So the volume is equal to, what was our volume equation again? It was this part here. Right, that's the optimal equation. So VW was equal to 5 over 2W minus W cubed over 4. So you're just going to go V, then that is the root of 5 over 3. Just type this all in your calculator, so it's 5 over 2 times by the root of 5 over 3 minus root of 5 over 3, that's all the root of 5 over 3 cubed over 4, and then you're going to get an answer of something like 2.15 meters cubed. All right, hopefully that makes sense to you. So just to sum it up again, the total surface area was our parameter. We found the optimal formula, simultaneous equations, find the derivative equal to 0. You only get actually one solution because other solution doesn't make any sense. You don't need to do a second derivative test, and you're finding the other dimension, and then you're finding the volume. Alright, so this question here, D, there's only one thing that, I'm not sure if you guys know this, but 1,000 cubic centimeters is equivalent to 1 liter. So if you have a box of, if you have 10 centimeters by 10 centimeters by 10 centimeters, some cube of that sort, well then that a liter can be filled with a liter, right? So 1 cubic centimeters is equal to a liter. So let's look at this question. A manufacturer needs to make a cylindrical can that will hold 1.5 liters. In other words, that is equal to 1,500 cubic centimeters of liquid. Determine the dimensions of the can that will minimize the amount of material used in its construction. Okay, determine the dimensions of the can that will minimize the amount of material used in its constructions. So what is being given to us? So given those constraints is the volume, right? So the volume is being given to us. What's our optimized function? The function we're going to find the derivative and later equal to 0 and then solve it. What's that going to be in terms of? That's going to be in terms of total surface area. So you need to just separate those two. It's been given to you is that constraint, the parameter in terms of volume, but you will need to find the minimized part of that is the amount of material, so that's the total surface area. Okay, so let's look at this. So the volume is equal to the volume is equal to 1,500 cubic centimeters. How would you find the volume of a cylinder? So that is of course with the base, right, and times the area of the base times by the height. So it's pi radius square times by h. So the volume is 1,500 is equal to pi radius square times h. Fear not if you see 3 variables. Remember, pi is just it just represents a number, right? So in other words, you've got r square h is equal to 1,500 divided by pi, right? So you're not going to find the derivative with respect to pi or something. That's actually just the number, right? Okay, cool. Let's go for it. So that's the first part. That is the constraint. Then we need to find the dimensions for which the can will minimize. So that's the total surface area. So what's the total surface area of a cylinder going to be? So if you want to paint the cylinder, what will you paint? Well, you'll paint that bottom part, so that pi radius square. And there's 2 of them, right? It's the top and the bottom, so 2 of them. Plus, so that's that part and that part, right? And then all the way in the outside, right? And what is the outside? Well, so first of all, this whole part around it, right? That will actually be the circumference, right? So the circumference, so times by then the height. So then you actually get a lovely rectangle like this. So this is the circumference then of that circle, okay, the base circle, and then times by the height. And what is the circumference of a cylinder? So it's 2 pi radius. That's 2 pi radius, and what is the height times by the height? Therefore, so you can say, for example, A and do you see we've got an R and an H? You need to decide which one you want to get learned. So if, say for example, I want only R's in my question, R, so 2 pi radius square plus pi 2 pi radius H, okay? And then we just need to get H alone in our constraint one, you know, the parameter one, so 1,500 divided by pi. So in other words, we're going to divide by r square on both sides, and then we just do simultaneous equations. So in other words, we just substitute this into into that baby. And then we just have it in terms of r. Don't let the pi again confuse you. So therefore we've got AR is equal to 2 pi radius squared plus 2 pi radius times pi 1500 pi radius square. And what is that equal to if we simplify that? It's 2 pi radius squared plus pi. So the pi's divide there, and r divided by r square is equal to just r on the bottom. So we've got 3000 over r, it looks like. And okay, so that is our optimal formula, right? That's the optimized equation, optimized function. Therefore, what are we going to do now? We're going to find the derivative of that AR and let that equal to 0. So the derivative of AR is going to equal to, and just you see there's again an R on the bottom. So that is then AR is equal to 2 pi radius square plus by 3000 r to the power of minus 1. So the derivative of that is going to be derivative of 2 pi r square, you're finding with respect to r, is you of course going to multiply the 2 to the coefficient, so 4 pi r, and then plus pi, but a negative, because here we're going to go minus 1 times by 3000, so it's minus 3000, and then r and subtract 1 from that, so it's minus 2. So the derivative of function AR is going to equal to 4 pi radius minus 3000 over r square. And that is where that's going to equal to 0, right? The derivative of AR is going to equal to 0, so 4 pi r minus 3000 over r square. So 3000 over r square is equal to 4 pi radius. What now? So in other words, what we can do is multiply r square on both sides. So 3000 is equal to 4 pi r cubed. Divide by 4 pi on both sides. So 3000 divided by 4 pi is equal to r cubed. And you just type that in your calculator and you find the square root of that. And what is that equal to? It is equal to 3000 divided by 4. Sorry guys. And the square root of that answer, and that is equal to 15.45 whatever this, what was it, centimeters. That was the radius. And what did they actually ask you? Did they find the radius? No, determine the dimensions. Okay, so that's the radius, and what's the other dimension which we need? We need to find height. So therefore the height, just substitute that back, is then 1500 divided by pi radius squares, in other words 15.45, all of that square, so that then is equal to, then you get 2 for that one. So therefore the radius is equal to that, the h is equal to that. That will maximize, optimize the material use. So to minimize the material use. Okay, I think that's quite a nice question. Okay, let's look at the next one. F. So you've been given a cardboard of 14 by 10, and then you're going to cut out those corners, all right, of h square each. So in other words, that h and that h, and so on. So all of those. So what happens now is your cardboard was originally say 10 by 14, and because you're cutting out those corners, that's h and h and h. So you, in other words, the bottom part of your cardboard now of the box that you're making, right? So there will be a flap there, and there will be a flap there. So this part here now would be that was 10, so it's 10 minus h, so that will be 10 minus 2h, and this part here would also then be 10 minus 2h, and then that part there, it was 14, so it's 14 minus 2h, and of course that's the same as there, right? So, okay, so, and then you just, so that's kind of the simultaneous equation part, right? So you now have the new base, the area of the base. So if you want to find the volume, it's length times breadth times height, and you've got now the length, so it's the area of the bottom, right, and times by the height. So that length and breadth I'm referring to is area of the base. And what you've got, you just keep on going until you've got this optimized equation, and you're very happy because it's in terms of h. And you've used the 14 and 10. Always just make sure you've used those parameters in a way. So then you're just finding the derivative, you equal it to 0, and you get two solutions. H is equal to that, or H is equal to that. Which one will it be? This is one of those great questions then where it's actually a good idea to double check with a second derivative, you know, just which if it's a smaller h or the bigger h, right? So if you work out the second derivative, so that will be the derivative of h, we say it was 12h squared minus 96h plus 140. The second derivative of h is going to equal to 24h minus 96. In other words, if you're going to substitute 1.9183 into there, you're going to get 24, 1.9183 minus 96. And so for example, that was 2, right? Then that would have been 48. So it's just going to be less than 48. Minus 96, that is going to be less than 0, right? You're going to get a negative answer there. Less than 0 means it's concaving down. So in other words, you're going to find a maximum turning point. And in the same sense, if you would substitute 6.8017 into the second derivative, it was 24 times by, what's it, 6.0817 minus 96. 24 times by 6, so for example, if you just take 6 is equal to, what's it, 120, 144 about, minus 96, there you're going to get, there you're going to get an answer that's definitely possible and positive. So therefore, if the second derivative of the point is positive, that means it's a smiley face there, concaving up, and you're finding a minimum turning point. So what did they ask you? To maximize the volume. So therefore, it's actually the smaller h. How cool is that? So therefore, h is equal to 1.9183. That will maximize the volume of that box. So yeah, and then did they ask you to determine the height of the box? Yeah, that's exactly it. Right, question G, a window is being built and the bottom of a rectangle, and the bottom is a rectangle and the top is a semicircle. If there's 12 meters of framing materials, what must be the dimension of the window be to let the most light in? Okay, so what we've got is if you're thinking of the framing, so it will be the H part, so it's that part, so it's the 2H, and then that 2R, right? And then it is the half circumference of a circle, right? But only half of that. That part is not included, so it's just a half circumference, and so it's a half times by 2 pi radius. So therefore, the total framing, so let's call it f, function f, is equal to 2h plus 2r plus pi r, okay? And then, so what do we know about the total framing? There's 12 meters. So, well, it's not 20, 12. So 12 is equal to 2h plus by 2r plus by pi r, okay? So that's quite cool. And then they ask you, so that's not an optimal formula, right? That is just some of the constraints, or the constraint that was given. So then they ask you, if there's 12 meters of framing, what must the dimensions of the window be to let in the most light? To let in the most light, of course, the greater the area of the window, the more light will come in, right? So please don't try to work at the volume of the window now. That will be not necessary. So therefore, if we want to get our equation with optimized area, it's going to be the area of the rectangle. So that is the base times by the 2r. Do you follow? So it's that part there. So that's the base plus by the 2r, and then it is half the area of that circle. So it's a half times by pi radius square. So in other words, so we've got the area formula, so A, so that's 2BR, HR, sorry, not H, or B, that's H. So let's just change that one, sorry, not BR, HR. So it's 2HR plus by pi radius squared divided by 2. Okay, Now we just need to do simultaneous equations, and you need to decide whether you want to substitute h into it, or if you want to substitute r into this baby from there to there. Okay, so I think it's easier to get h alone. So 2h is equal to 12 minus 2r minus pi r. All right, so therefore we can just say the area is equal to, and remember we substitute, we substitute this all into then the 2 pi there, 2h. So do you see there's a 2h, just substitute that in. So in other words, what we've got is we've got 12 minus 2r minus pi r times pi r, okay? So that's 2h. Plus pi r square over 2. So what we've got is we've got 12r minus 2r square minus pi r square plus pi r square over 2. So, and then we need to get, well, we need to find the derivative in terms of r. So let's just write this function. So that is ar, 12r minus 2r square minus pi r square plus pi over 2 r square. You can simplify, there's actually like terms there. You've got the minus pi r square plus a half pi r square is going to of course equal to minus pi r square. But if you didn't see that immediately, because that is a bit of up a notch, so you can find the derivative. So that's 12 minus 4r minus 2 pi r plus pi, and then 2 times pi over 2 is pi. So it's pi r, and you let the derivative equal to 0. 12 minus 4r minus 2 pi r plus pi r. And what is minus pi r plus pi, what did I say? What's minus 2 pi r plus pi r is equal to minus pi r. So therefore, again, now what do I do now? I can take out r as a common factor. So you can put all the r's on one side. So 4r plus pi r is equal to 12. Take out r as a common factor. So it's 4 plus pi. So therefore, r is going to equal to 12 divided by 4 plus pi. And 12 divided by 4 plus pi is equal to 4 plus pi is equal to 1.680, and so on. So that's 1.6802, and so it goes on. All right, and then you just need to find h. So remember we've had 2h is equal to 12 minus 2r minus pi r, and so therefore 2h is going to equal to 12 minus 2 times pi, that baby, 4 plus pi minus pi times pi, 12 over 4 plus pi. You type that on your calculator, and you actually also get h is equal to 1.6802. So that's quite, I think that's quite cool. So that's actually also going to be the case when r and h is the same. So therefore that will make a rectangle there, because if r and h is the same, so that means that part there would be half of that distance. So yeah, so that's I think that's quite cool. Lastly, we're going to look at this question. Determine the shortest vertical distance between the curves of f and g if it is given that there's this parabola and then there's this hyperbola. Okay, so what do we do again? We look at which function is on top. So the hyperbola is on top there. It's a bit of a squeaky one, but anyway. So g is the hyperbola, and then we've got f, that is the parabola. All right. So which function? So if we want to find the shortest distance, okay, between those two graphs, where do you think it will be? Somewhere here. Hey, it looks like it. Shortest vertical distance, of course. So they must have the same x values. What are you going to do? The shortest distance, let's call it the v for vertical distance, is then going to equal to, it's the g of x graph, the one on top, the one with that highest y values, minus the one on the bottom, the f of x. Alright, so v then is going to equal to g of x, which is 8 over x, minus the g of x, which is then, just be careful of brackets, right? of including brackets rather, just be careful of the sign. So that is plus x squared minus 2x minus 3. So in other words, this is then vx into the vertical distance in terms of x. And just let's do this to the power of minus 1 just for now, because we're going to find the derivative of that, right? So what we've got is we've got the derivative of v of x then is minus 8 x to the power of minus 2 plus 2x minus 2, right? And then that is equal to 0. Remember, how do you optimize it? Find the derivative equal to 0 of minus 8x minus 2 plus 2x minus 2. So that becomes minus 8 over x squared plus 2x minus 2. So what I do, multiply every single term by x squared. So 0 is equal to minus 8 plus 2x cubed minus 2x squared, it looks like. So just rearrange a bit. So therefore 2x cubed minus 2x squared minus 8 is equal to 0. And then we solve for x. You can actually see that if x is equal to 2, your remainder there would be 0. So x is equal to 2. The other solution are non-real. So that's actually the only real solution that's possible there. So at the point when x is equal to 2, the distance between those two graphs will be at a minimum. So, and then they ask you to determine that shortest distance. Now, what would you do now? So, where's your function then? So, we've got your vertical distance is equal to, what is it? 8x minus 1 plus x squared minus 2x minus 3. So, at 2, so that's 8. 2 minus 1 plus 2 squared minus 2 times by 2 minus 3. So, that is at 8 over 2 plus 4 minus 3. What is that equal to? That's 4 plus 4 is 8 minus 4 is 4. It's 1. So then the distance is equal to, is 1.